Okay, so today we are going to talk about the Einstein tensor, which is exciting because it's the last step we need before we can talk about the Einstein equation and then go ahead and solve the Einstein equation. So the Einstein tensor is in fact a curvature tensor. So that immediately means that it flows from the Riemann curvature tensor. This guy is the granddaddy of all curvature tensors. And we've been spending lectures and lectures upon lectures studying this guy and its various metric-induced contractions. Although going from the Riemann curvature tensor to the next important tensor, which is the Ricci tensor, that's actually not metric-induced per se because you just contract over these indices as they already exist. But to go from the Ricci tensor to the curvature scalar, that is metric induced because you need to raise an index to execute the contraction. Anyway, the point being that I guess in some sense they're all really metric induced, but all of these guys are related to the curvature tensor. This is the object that we studied the most, and then we just learned how to, we studied the heck out of this and we interpreted what it means. We spent more time interpreting it because defining it's very simple, right? Defining it is just, contract the curvature tensor, the Riemann curvature tensor, over the first and third index, and boom, you've got it. So, defining the thing is the height of simplicity. Interpreting it took us, I don't know how many lectures, 10 lectures? It was kind of ridiculous because, an interpretation is supposed to make things easier, right? You're supposed to say, now I kind of understand what it means. And we did get there, but to prove that the interpretation was what it was took a lot of effort. And then to go from here to here, I think it took just about as much effort, right? So, but we've done it. The point is we've done it. This was easy to interpret. As we built it and constructed it, we interpreted geodesic deviation, and then this one and this one we interpreted as, let's see, do I have it here? Yes. These are the formulas that we ultimately landed on to interpret the curvature scalar and the Ricci tensor. I'll just remind you of what they are. We could look at, say, I think this is a good one here. These came from the two papers that I've been recommending, right? Where are those two papers? These two papers, right? These are excellent papers, and they really refreshed my understanding and deepened my understanding of these things. So simple, but these are good papers. Check them out. But these two formulas are where those papers ultimately land. And let's just looking at this one where epsilon is the geodesic distance that we're dealing with, right? And this is basically saying that the limit as the size of a small volume in space-time gets small. That's what that limit is. Let me blow this up. That the limit as the size of the volume gets small, the acceleration of that volume as it moves through space-time, right? The acceleration of the change of volume, of a volume element, relative to what its change, relative to the volume itself, the change it would have in relative to the size of the volume, right, is given by this expression, the Ricci tensor contracted into the 4 vector of the velocity of the volume element. So the idea is that you have a little volume element in space-time, and it's got a little 4 vector velocity in space-time, and this volume starts to change. It either gets bigger, maybe it gets smaller, but the acceleration of that volume change is what this guy captures. And in flat space, it could change, but it won't necessarily accelerate its change. Its change won't accelerate in flat space. But in curved space, the volume change could accelerate. And we should remember, like, if this is a volume in space-time, right? Say we have x, y, and let's see, x, y, and z, right? we're just looking at it sitting there in space. But of course, it's got a 4 velocity in time, right? So it's, even if it's sitting there in space, it's moving in time. So its 4 velocity in time is something with a component in the first slot and nothing in the second, third, and fourth slot initially. That's its initial 4 velocity in time. So if we just sort of watch this thing, we might see that it just gets bigger and bigger and bigger, right? Or we might see that it gets smaller and smaller and smaller just in front of us if we're in the right kind of coordinate system. The one I'm thinking of, for example, is, say there's some sort of planet here and you're floating up above the planet and you're looking at this volume in front of you and you're both falling, right? Well, you feel like you're in flat space, right? Your impression and your reference frame is flat space in the local lab. But globally, this is curved space-time, and you're going to see this sphere get smaller and smaller and smaller as you get closer toward the planet. It will be a very tiny effect, right? But it will happen. And that acceleration of that shrinkage, that's the way we interpret the Ricci tensor. And then the curvature scalar, let's see, which these are both the exact same equation. I think I prefer this one here, actually. I think I prefer this version. But it basically says the volume of a little element in curved spacetime is equal to its volume that it would have in flat spacetime minus this little correction term where n is the dimensionality of the spacetime and lambda is the size of the volume, is the radial size of the geodesic radius of the volume. So if this is your volume, lambda is a long sum geodesic. And we analyzed the heck out of this. And this is a very, the volume in curved spacetime is going to be different than the volume in flat spacetime. That was the whole point of all of those lectures we did. So we ended up with these two equations, and we feel pretty good that we understand, I certainly do, pretty good that we understand this material. And when I say I do, and you guys get all cynical about it, well, you're teaching this stuff, it's hard for us. I got to say it's hard for me too, right? I've been doing this a long time. These subjects don't come up very often, and I remember and forget and remember and forget. I mean, I constantly tell people, don't be freaked out if you've I used to know this, or I understood this for 5 seconds and then kind of lost the bubble on it. That's just how it is. That's just, unfortunately, human brains just don't work very well. And you have to kind of do this over and over again. So this is sort of a review of the last 20 lectures. By the time we finish this, I couldn't have reproduced the proof for the interpretation of the Ricci tensor, right? I would have to go back and review it, right? This isn't like memorized stuff, right? That's why it's so nice to have good papers and good books that you're familiar with, that you can go back to and rediscover things. That's how this material is learned and worked with, Anyway, okay, so we've got the bead on those two things, on these two objects. And what we're going to discover is that the Einstein tensor is constructed out of these two objects. So the Einstein tensor is another curvature tensor, but it's not something that we have to derive. We're going to find that ultimately it's a combination of this and that. And we have to understand, okay, well, why bother to do that? So that's what we're going to learn here. But this is less a matter of interpretation of something than defining it. But we should, before we move on, take a chance to reflect on the significance of the curvature tensor and its origin, which comes from the connection, right? And remember, this connection, this is our geometry. This connection is the ultimate expression of geometry on a manifold. The fundamental theory of general relativity is that everything happens on some sort of manifold of space-time. And because it's a manifold, I draw it like this because that means we have coordinates, right? x0, x1, and then x2 and x3 are suppressed here. But once you know it's a manifold, you know you have coordinates. When you have coordinates, you have tangent spaces. But these tangent spaces, the only way you can kind of understand how this is all bound together in something that can be called geometry is if you impose a connection on the manifold. You have to add that to the manifold. And you could add it arbitrarily, right? If I just pick these numbers, right, there's going to be 4 times 4 times 4 numbers, right? If I pick these 4 numbers, or these 4 times 4 times 4 numbers, I've got myself a connection. And I can pick them completely arbitrarily, right? There's no restriction on doing that. The point being, though, that the question is not what do I want those things to be, but what does nature want them to be? And nature chooses the connection after choosing the metric, right? The metric is what exists on the manifold by nature, right? This is where the Einstein equation delivers us a metric on the manifold. That's where the physics is, right? And then once this guy exists, it selects of all the possible connections that you could just arbitrarily drop on a manifold. It picks out the one, and that's going to be called the metric connection. The metric connection. Sometimes it's called the Levi-Civita connection. But regardless, that is forced upon us once we have a metric. There's definitely a connection. If your manifold is rich enough that it has a metric, well, or is endowed with a metric, right? Then it's automatically endowed with a connection, right? And this is a metric tensor, of course, right, which is a tensor applied to every position on the metric. So this metric tensor is G mu nu dx mu tensor product dx nu, right? And G mu nu is a function of space-time, right? So there's going to be these 16 components of the metric located at each point. Each point will have its own value of the 16 components. And the coordinate system and the basis and the tensor product space, all that is now part of our DNA, right? We understand all of those things. But this metric gives us, the point being here, that this metric, very, very important, gives us the connection. The connection gives us the curvature tensor. The curvature tensor gives us these Ricci tensor and curvature scalar, and it gives us the Einstein tensor. All right, so how do we understand the Einstein tensor? So now we're kind of caught back up. Let's move on. All right, so we are now going to talk about this blue point, which lives in a three-dimensional space. So this blue point looks around and it sees a three-dimensional space. Now, this is not space-time we're talking about. I think the way to understand how this all works is to just sort of stick to straight-up geometry. So it's hard to do that because we anthropomorphize things so much, and we can't imagine living in a world without time. But this is just a three-dimensional straight-up space, and it looks around and it wonders, is space curved? Is, at my location where I am, is space curved? Is my three-dimensional space curved? Let's call these three-dimensional space the blue point lives in, let's call M3. We'll call it M3. Is M3 space curved? 3 for the three dimensions of it. Now, we know how this process is done because we spent all those crazy lectures on it. But what this little blue point is going to do is it's going to construct a sphere around itself, and that sphere will enclose it. And the way it constructs that sphere is it runs straight lines, right? What it perceives as straight lines to all the little points on the sphere, and they'll all have the same distance, lambda, and it constructs that sphere, and then it measures the surface area of that sphere, and if it doesn't get 4 pi lambda squared as the answer for the area of the surface of the sphere, it's the sphere is, by the way, it's S2, right? It's just the surface. If it doesn't get 4 pi r squared for the volume of S2, which is the surface of a sphere, two-dimensional area, if it gets some other number, then it knows that It's in curved space-time. And the number it will get, the actual number, will be something like the volume that it measures over the volume it expects is going to be something like 1 minus some constant times r, where r is the scalar curvature. So this is a way it can kind of get at and measure that scalar curvature. Right, so that's that whole process. Well, that's the hard process, right? So what's the sort of general relativity way that this point would do this process? Well, in principle, what's going on is whatever three-dimensional, what it's curious about its own three-dimensional space, right? So we're all talking just straight up space geometry. So the three-dimensional space is curved. So he's imagining that it's embedded in R4, actually. So the three-dimensional space is curved in R4. Now, R4 is Euclidean, so it has a Euclidean metric. So this is just very classic sort of higher dimensional differential geometry. So it's got this metric, and I'll write it in blue, G mu nu. But this is the Euclidean metric, so it's like delta mu nu, right? And whatever the surface, or I call it a surface, but the three surface that the point lives in, because remember, the point sees itself in a three-dimensional manifold, and it now has measured, it's determined through its measurements that this three-dimensional manifold is not flat. Well, what does that actually mean? Well, that means that, and we did this in the lecture just a little while ago. I think the last lecture, some lecture I did recently about the pullback and push forward, right? We talked about this, but the idea is this Euclidean metric, this three space, M3, right? This is M3. It's embedded in R4, which means there's a mapping from M3 to R4. R4 has a metric. So the metric, G mu nu, that's in R4, gets pulled back to G, say, hat mu nu in R3. So if M3 was totally flat, then this embedding would be the identity embedding, and this pullback would be the identity pullback, basically. And that's not right. The pullback would just be flat Euclidean space in M3, right? But this mapping is not the identity mapping. The M3 is actually mapped in such a way that we have some curvature going on. So the pullback, or M3 structure, is such that when mapped into R4, the pullback is not the Euclidean metric. The pullback is some other metric. So now we have a metric, though, in M3, right? And I'll call that metric G mu nu hat, right? So M3 has its own metric, therefore it has a connection, right? And therefore it has a Riemann tensor, right? R4's Riemann tensor is 0, right? R4's Riemann tensor is 0 because it's R4 we're calling flat space, right? But R3 has an induced metric, induced from the flat space of R4, but M3 itself is curved in R4, so the pullback of this thing gives us a metric in M3. So now, okay, fine. So that's this whole story. But now we can figure out with this process, if the blue spot knew about all this, and if the blue spot knew its own metric, then the blue spot wouldn't have to do all these measurements. Basically, the measurements have already been done, and they're sort of embedded in the curvature tensor. And all the blue spot has to do to figure out the curvature of its local area is calculate R, which is GAB of RBA. And then, of course, RBA is just equal to R, I guess what would be R alpha alpha BA, right? So you would contract on the first and third slots of the Riemann tensor to get RBA, and then you raise B and sum out. Well, basically, you fully contract RBA using the metric tensor, and you end up with the curvature. And if this thing isn't 0, then there's curvature in the space-time. And that's all driven by this metric. Okay. Now, all right. So that is pretty easy to grasp. So, what's the next step, or the next step in this description that I'm trying this lesson I'm trying to teach? So, the point P could ask, well, wait a minute, I want to know something else. There's another manifold. M3 is certainly a manifold. It's the manifold I live in. But there's also a manifold that I perceive as a plane that cuts right through where I live. So I live in this plane, and I'm going to call that M2. And it's a two-dimensional manifold. And it has, it's fully embedded in M3. And as far as I'm concerned, it looks flat. And the reason I know it looks flat is because if I take a tangent, if I take a vector in my tangent space and I parallel propagate in the direction of that vector, then that vector stays in this plane, right? There's two orthogonal vectors. I got to do this systematically. I can find two vectors. I can create M2 by taking two vectors in my tangent space and using those two vectors to shoot geodesics in two different directions. And I can do this in every different direction. I can take linear combinations of those two first vectors, and I can do it in every direction. And I will end up with what looks like to me to be a flat plane, because everything is geodesics. Geodesics that are linear combinations of these two vectors. So let's say that's one of the two vectors, and that's the other two vectors. Everything else, I take the locus of all the different geodesics that emanate from me, from my point, the point P. Well, I guess I'm calling it the blue point, right? I take all the geodesics that emanate depart from the blue point that are linear combinations of, say, what I'll call vector A and vector B, right? So that's no good, because I should do vector V and vector W. So any vector that's A, V plus B, W, normalized. Let's presume that it's normalized too. So V is normalized, W is normalized. Then we take this linear combination, assume it to be normalized. Whatever that combination is, we create that geodesic. And the sum of all these geodesics, not the sum, but the locus, the collection of all the points on all these geodesics, define this plane that we now call M2. And M2 is clearly a submanifold of M3, right? So we could ask the question, well, M3's has a metric, G mu nu, right? G mu nu hat. And that metric is not flat. It's not Euclidean metric, because remember, flat in this story is Euclidean, right? This is all completely transferable to the Lorentz case, right? So flat space-time, this would be 4 dimensions, and Lorentz, so the R4 would have been flat, but 1 dimension would have been time, so this would have been a Lorentz space-time. But right now we're just thinking, because it's all the same reasoning. So, but G mu nu is not flat. The metric in M3 is not a flat metric, because M3 is curved in M4. So now we can ask the question, well, wait a minute. If M3 is curved in M4, is M2 going to be curved in M3? Or what is the curvature of M2? Right? Now the process of finding the curvature in M2 would be sort of the same. It would be going out some distance from the point P, but now you're just dealing with this circle, because you're the blue point, you know about 3 space, but you're pretending you only live in 2. And then you would measure the area of this S1 chunk, and you would compare that to the number 2 pi r, right? 2 pi lambda, right? You would compare it to 2 pi lambda. And if it was bigger, you'd have a negative curvature. And if it was less, you'd have a less curvature. And from that, you can infer the value of the curvature r at P in M2, right? So the idea is that the point P is asking the question, I want to know the curvature of a piece of the space I live in, a submanifold of the space I live in, and a specific submanifold, a submanifold that looks like a plane, right? That was what this geodesic construction was. So I'm interested in the curvature of the submanifold of M3 that is orthogonal to this vector S. I'll call it S. So there's a vector S, and V and W are orthogonal to S. And V and W can make this plane, that's M2. But I can describe M2. I don't need V and W to describe M2. I really only need S, because V and W are orthogonal to S. And orthogonality means something because M3 has a metric G mu nu. So I know that if V and W are orthogonal to S, then S mu V nu, for example, that'll be 0, right? Because that's what orthogonality means, right? Orthogonality literally means that this calculation will give you 0, right? And that would also be true for W nu, right? So those two are orthogonal. W and V do not necessarily have to be orthogonal, by the way, but for the purposes of this, we'll say all three of these are. So the question I'm asking is, what is the curvature of the manifold that is orthogonal to S, all right? So now we know the quick calculation. We did the quick calculation to figure out R at P, but that R was the curvature of M3, right? That was just the full contraction of the Riemann tensor calculated at P. So how do we go about calculating this other number, the curvature of M2 at P? So what we need to be able to do is find vectors that are orthogonal to other vectors, right? And the expression that is going to drive this is this expression right here, G mu nu minus S mu S nu. And we're looking for orthogonality relative to S. And I'm going to demonstrate how this object does the trick, right? So the first thing to understand is we're choosing the orthogonal vector. Remember, this is S, right? So S is going to define the submanifold for which we are interested in the curvature. And S has is normalized, right? So this is what we mean by S is normalized, right? S is normalized to 1. So if I took a structure G mu nu minus S mu S nu, notice this is a totally legit tensor equation. Even though this has two indices, this has two indices also. I'm going to review a few of these facts just in case you've forgotten, but that is an actual rank 2 tensor right there, a rank 2 covariant tensor. So now let's take that thing and let's contract it. Let's contract one index with another vector in the tangent space, T nu, right? And this contraction will just be very simply done. This part here, oops, oh no. This part here contracts with that, and by definition, that contraction gives you the covariant version of T. And then this, there's nothing obvious to, there's no similar process, so you just bring it in, and here you have what would look like to be a mixed tensor, but remember, that's a dummy index, right? So that doesn't count. So you only have one free index, so you have, this is a covariant vector right here. This is a covariant vector. And I want you to see that this covariant vector, what's left over after this guy is orthogonal to S, right? This vector here is orthogonal to S. So this is a way to create a vector that's orthogonal to S. So I guess it would be, in sort of engineering terms, this thing that's left over is the projection, well, it's the vector T minus its projection on S or something like that. It's orthogonal to S. But how do we know that? Well, we know that because what we're going to do is we're going to find the dot, essentially we're going to contract it into S, and it should end up being 0, right? So here we have S, the contravariant form, and we're going to multiply it by this object, which I argue is orthogonal to S. And then I expand this the same way. So this guy comes in and it forms T mu S mu. Remember, that's a dummy index. So this guy here is a number. So this side here better be a number 2. Well, these are all numbers, so they commute and everything, but I'm going to keep the order initially. So we have S mu, S nu, T nu. That's a dummy index, and that's a dummy index 2. Well, let's rearrange everything, and you get T mu S nu. And then I brought this S nu in here like that, and I got S nu, T nu. This guy is 1 because we dealt with a normalized vector. And so we have T mu S nu, T nu S nu. These are dummy indices, right? So the value of these two things is identical, right? It's the same value. They're both real numbers, and therefore they subtract to get 0. So this is 0, which means this vector was orthogonal to that vector, okay? So this guy is really a projection, right? And we're going to call this, I'll hold off on calling it that, but this object here will project out the portion of T that is orthogonal to S. So now things are actually kind of simple once you understand that, because normally what we would do to find the scalar curvature around a point is we would take the curvature tensor, alpha, beta, gamma, delta, and I would force its contraction. Well, let's see. That's actually not the best way to write it down. I would probably do it like this. I would go alpha, beta, gamma, delta, right? And we want to contract on all the indices. So we want to lift alpha and turn it into gamma. So we write G alpha gamma, and we want to lift, I think, beta and convert it into delta. So G beta delta. The order of alpha and gamma and beta and delta, that doesn't matter, because remember, this is symmetric. I think it's a little more typical. The one you want to raise, you would put on the right. So this one, I want to raise beta. See, I probably, bad form, probably because it blends the eye better. I would do delta beta, and I would do gamma alpha, right? I just swapped the order. But either way, what I'm doing is I'm raising alpha and making it gamma, and I'm raising beta and I'm making it delta, which will give me R gamma delta, which is basically, well, it's a full contraction, so it's R, right? So that's how I would normally do it, right? So, but how are we going to do it this time? Let me get back to normal here. Okay, that's the way we normal. Well, what we're going to do is we're going to replace these two things with these projections, right? We're going to project off the parts that are orthogonal to S. And then that will give us our answer. That will restrict this whole process just to the plane that is orthogonal to S. Let me make sure I say that correctly. S is this vector that's orthogonal to M2. So we only want the parts of the calculation that are orthogonal to S, which means we want the parts that are parallel, right? Parallel to well, we want to project off the parts that are parallel to S, I suppose is the way to say it, and we want to keep the parts that are orthogonal to S. It doesn't really matter how to say it. Well, you do got to say it correctly. You don't want to say, I want to keep the parts that are parallel to S, because that's the opposite of what we want to do. Anyway, the point being is that we're going to replace these two guys with these two guys, where S, with this, where S is the vector in the tangent space at P that is orthogonal to the manifold we care about. So I'm going to write this down in the new way. See, this guy here replaces that, and this guy here replaces that, and then I just need, I think I just need one more copy of this right here. And this is the guy that we're now going to calculate, right? We're going to execute this. Normally, this first one's really easy. That contraction just gives you R, right? This one, it's not clear what's going to happen, right? But let's see what happens. I will write down each of these steps and then reveal them one by one. All right, so the first step is, it's just a simple expansion, right? We're just taking this term, and everything's multiplied by this term. So that gives you this expression right here, which you can already see what's going to happen with that guy. I'll show it to you in a moment, of course. Then you have these cross terms that pop out right here, again with this factor. And then you have another factor out here that is just this times this times this. Wait a second, that last factor, that's not correct, right? The last factor should be this times this times this. So let me fix that. All right, so I actually put this back in here. Ignore that red line for a moment, but I got these S's in here. So all these, the S vectors come up, the negative signs here, this negative sign on the right and this one on the left combine to give you this positive sign. The cross terms, I'm adding and subtracting them as they're grouped. So what's the next step? The next step is to notice that this first term is simply the curvature as you would have normally calculated it, right? This is the curvature at the point P of the entire three-dimensional manifold of M3. So that's what that is. These cross terms, if you take R in and you multiply the first of the cross terms by R and the second of the cross terms by R, you realize everything's a summed up dummy variable. So this term here and this term here just add together to give 2. And since you're subtracting, you get minus 2 times S delta, S beta, R alpha, beta, gamma delta. This term is equal to 0, very conveniently. And that has to do with the fact, first of all, this is completely symmetric, right? S delta, S alpha, S gamma, alpha, delta, S beta. That is a symmetric term. You switch these two around, or you're always going to get the same number. This is not symmetric, right? If you switch alpha and beta with delta and gamma, well, there's anti-symmetries in this thing. That's all that matters. There's an anti-symmetry there. If you swap alpha and beta, then this becomes this whole thing becomes negative, right? If you know, it's funny. Like I said, you always forget this stuff. I knew my symmetries of the Riemann tensor cold, when I lectured about it, and now I'm kind of rusty. But I do remember if you swap the first two indices, you get a negative sign. I think if you swap the second two, you get a negative sign. But if you swap the first two with the second two, then it's actually symmetric under that. But the point is if there's any anti-symmetry, you ruin and you completely contract into something symmetric, the whole thing's going to be 0. So that goes away. So all that's left is this, right? All that's left is this. So then what we'll do is we'll take the metric and we'll go ahead and raise alpha using the metric to get an upper gamma here, which contracts with the lower gamma to give you the Ricci tensor. So that's kind of nice. So now we have an expression. Remember, this expression is the curvature scalar of the submanifold that's orthogonal to S. Well, the answer to that is the regular curvature scalar of the whole manifold minus this piece, right, which has to do with the Ricci tensor. Kind of interesting. So what next? Well, then what we're going to do is, remember this has been normalized to 1. So I can insert this expression right here on the left side next to r without any there's no implications to that. This thing equals 1. It's fully contracted. It's a number. It's equal to 1. But the point is now I get these s's here and here, and I can pull out the vector that defines this manifold I'm interested in, and then I'm left behind with this, right? And this is equal to the scalar curvature of M2, right? That's what this thing is. And what's interesting is the scalar curvature of M2, it's a number, right? This is a single number, but that's a vector and that's a vector. And to make that a number, to gobble this up, you need a rank 2 tensor here. Well, that's what you've got. You've got the Ricci tensor and you've got this metric tensor, right? The difference between those two is a rank 2 tensor. So that's just a rank 2 tensor. And what's important about that is there's a rank 2 tensor out there that when multiplied by the vector that defines the submanifold, that's orthogonal to the submanifold, gives you the curvature just of the orthogonal submanifold. All right. So let me rewrite this. So here I have it again, and now I'm going to take this part, and I'm going to define it to be a new, I'm going to give it another name, right? I'm going to call this 2, well, let's see, I think I'm going to call it, minus 2 G beta delta, and then this will be S delta S beta, right? And that is going to be the scalar curvature of this M2 thing. So by doing this definition with this minus 2, what I'm really saying is G beta delta is equal to G beta, did I get this right? Is R Ricci tensor minus 1/2. Yeah, so this is right. So the minus sign let me swap the sides here. So I had the Ricci tensor over here and R over here, which is what I got. And then the 2 puts a 1/2 there. Okay, so this is convention, by the way. This definition, defining this piece to equal minus 2 times G is convention. And this, of course, if you don't know already, that is the Einstein tensor. And as you can see, this Einstein tensor is nothing more. Well, that sounds like it's not important, but the Einstein tensor is that tensor that will tell you what is the scalar curvature of a slice of the manifold, in this case M3, that is orthogonal to a certain vector. So it's the orthogonal, it's the curvature orthogonal, the curvature in the manifold that is orthogonal to a given vector at a point. So I go to a point in the manifold, I choose some vector in the tangent space. In this case, I call it S. That vector in the tangent space defines an orthogonal manifold. And now what I want to know is at this point, what is the scalar curvature of that orthogonal manifold, given that the overall manifold has a metric of G beta delta, right? And the Einstein tensor is the thing that tells me that. So notice this is not a new variation per se on these overall curvature tensor, right? Alpha, beta, gamma, delta. Often it's listed that way, like in Meissner, Thorne, and Wheeler, the legendary textbook Meissner, Thorne, and Wheeler. It talks about all the variations or all of the things you can derive from this guy, and the Einstein tensor is certainly one of them. But what you're really, these two, to my mind, this is all pretty subjective. These are the things that are more fundamental, right? The Ricci tensor and the scalar curvature. The Einstein tensor is a way of expressing something else. But the fact that it can be reduced to these two is, I think, really, really important. And it's also, I don't think you would ever write the Ricci tensor in terms of the Einstein tensor, for example. But the Einstein tensor is in a critical combination because ultimately, remember the Einstein equation, this little foreshadowing, G beta delta equals some constant, right? Some constant times T beta delta, where this is the stress energy tensor. What you're basically saying is that the stress energy tensor is directly related to the orthogonal, the curvature of space in a direction that, of the curvature of a slice of space-time, right? So, well, we'll talk about that when we talk about the Einstein equation per se. I mean, but we're almost there. I mean, this is the Einstein equation, right? So that doesn't take too much thinking, right? You could just, if you take the Einstein equation, you contract with some vector at a point, right? What it's basically saying is that the curvature of space at that point, orthogonal to that vector, right, is equal to the number you get when you take the stress energy tensor and contract it in with the same vector, right? Now, we haven't talked about this, so interpreting this might be a little bit of a thing. But look, this is matter, right? And this is space-time, and this is the curvature of space. It's a literal statement that the curvature of space, at least orthogonal to a certain vector,
16 hours.
is directly related to the matter, right? And that is the Einstein tensor. Okay, pretty simple stuff this time compared to the others. We got through in one long lecture. And when I come back, we'll briefly look at the Einstein tensor, Einstein equation, and set ourselves up to solve for a symmetric space-time and do the simple